they immediately think that, well, then you need to bundle all these different VMs, you need compilers from all the languages to one VM or maybe a few VMs, they know how to communicate with each other and so on. And that's the moment when we roll our eyes, right? That's when we have an unfair advantage in the field, which is that we know you don't need all those. Once you have a formal semantics of the programming language, that's all you need to execute programs.
All right, welcome back. It's the 8th episode of Proofcast, and today I'm joined by two CEOs and two legends. Everett, it's nice to have you back, the current leader of RV, and we have Grigore Rosu, the former CEO of RV and the current CEO of Squared. Grigore, thanks for joining us.
Thank you for having me.
Yeah, this is awesome. I've been excited about this. I've wanted to learn more about Squared for a while, as well as some questions about early days at RV that obviously I wasn't here for. So this is going to be educational for me for sure. Yep. So, Grigore, you've been at the intersection of like formal methods and real-world systems for a long time. But I'm always curious, like, what was your first foray into crypto?
Well, yeah, I've been in formal methods for all my life because that includes mathematics, which is what I've done before. Crypto, I think my first contact with crypto was through one of my students back then, Philip Dayan, who worked at RV, and he got a bonus because he had a junk car. I thought that he deserves a better car, right? So we gave him a bonus, and he didn't buy a new car. He bought more Bitcoin. And I said, what is this thing? And then he explained me what it is. And I said, okay, whatever. That was my first contact, I think back in 2015 or 16. And then in 2017, I got more serious about it because I realized that, hey, this makes a lot of sense on all fronts, not only technical and programming language and formal methods, but also social, philosophical. It fit my, system of beliefs pretty well. And I got hooked, and it's everything since then.
And I know you've mentored quite a surprising number of people who went on to play pretty major roles in crypto, and including Everett, by the way. So maybe you guys could shed some light on the early days of working together.
Yeah, I mean, I can tell you my version of it. I'm sure Grigore has a different version, but I don't think actually, I don't know if I ever took a class with you actually when I was at the University of Illinois.
No, but you've been in many of our group meetings.
Right, yeah. I would attend your group meetings and I would derail them with my very strong opinions about the correct ways to do things.
Well, that's how you can find strong people, They usually have strong opinions. It may look bad initially, but long term, that's very important, actually. They have strong opinions. But of course, also be flexible, and Everett is. Yeah, but it was an amazing group back then. Philip Dayan, I mentioned, was part of the group. Then also Ilong Lee, who now founded and runs Mega ETH, was also part of the group. And we were all doing formal methods, programming language semantics, just doing things the right way. We never thought that much about crypto back then, initially. Then crypto just came into the picture, and it was just the right thing to work on with the right set of tools that we developed. It was never like we planned for crypto. It just happened. And I believe that we had the right tools to approach the field. The field was in desperate need, actually, of such tools, of correctness, of security. And we had those, and we approached them from different angles. Then, of course, everybody followed their path afterwards. We remained very good friends and strong collaborators. But yeah, so sometimes I think the moral here is that if you work on the right problems, then applications will come.
Yeah, I think it also helped that Andrew Miller was at UIUC as well and was able to kind of provide some guidance and let us know what was important or not. And then somehow we got the attention of IOHK at the time too, and I can't remember exactly how that happened, but it led to both some work at the university and at the company for.
Yeah. I remember Charles Hoskinson sent us a message. He said, "Hey guys, do you think you can use this thing yours, the K framework to do security auditing. Then I said, okay. First, I said, who the heck is Charles Hoskinson? So I said for him, and I said, okay, he's legit. He knows what he's talking about. Then, what is security auditing?
Yeah.
I know that sounds ridiculous, but back then I had no idea that we were doing security auditing, or at least that's how it was called. And then said, yeah, he's right. Actually, this makes a lot of sense. And we started very good, very solid collaborations with IOHK and Charles Hoskinson. Charles Hoskinson visited us right in Urbana a couple of times actually with his team. So it's very, very solid collaboration. So yeah, so somehow lots of Web3 activity happened at UIUC or around. Oh, by the way, Anatoly Yakovenko, who founded Solana, also a graduate of our university. I didn't work with him, but he's from our department. And also Sreeram Kannan, who founded EigenLayer, also from UIUC. And ironically, also Pramod Vishwanath, professor in DC department. Now he moved to Princeton. He, also, actually he was Sreeram Kannan's advisor and many others. So yeah, so it just happened that a lot of Web3 activity happened at UIUC without even having any course whatsoever on blockchains being taught at university. I proposed this semester, now this is the finals week, but this semester I proposed for the first time in our department on a blockchain course, a generic blockchain course. I didn't even have any idea what to teach when I proposed it, but I said, okay, we must have a blockchain course. Blockchain makes sense as a field. And then immediately, like in 5 minutes, the class was full, and then the waiting list also full. So it shows demand. Students really want this, and now we're offering it. It's it's here to stay.
When I was there was I think there was some sort of applied cryptography course that Andrew Miller was teaching, and that's actually how KVM started. That was kind of one of our big first forays into crypto with the K framework. And my roommate at the time was taking Andrew Miller's class, so I wasn't even in the class. But he came to me and he was like, "Hey, could we make a formal model of this EVM music?" Because at the time I was very much into formal methods, and I just would rant to him about it all the time or whatever. And he was like, "Hey, can we use that tool that you kind of know and have been working on to make a formal model of the EVM?" I was like, sure, I'll help you guys do that. And I kind of ended up doing the whole class project for them, for a class I wasn't even in. And I went to the presentation at the end of the semester as well and joined the class for that and talk to the people there. But that's kind of what got KVM started. And then I think it was after that semester that Charles Hoskinson reached out and kind of saw hey, there's actually some traction here. So that's kind of cool. And then I can't remember exactly, but there was also the MakerDAO guys, the DApp Hub folks. They came out to Urbana as well to learn how to use K to do the formal verification of their multi-collateral DAI, which was one of the biggest formal verification. It was the biggest formal verification effort at the time.
That's really interesting history. So was it KVM that was the first crypto project at RV, or was it Charles Hoskinson and the audits with him?
Both at the same time. So KVM and funded also by IOHK and Charles. That's how we started.
Yeah. The initial work that Charles Hoskinson and IOHK funded was based on this semantics-based compilation idea that we had, which we're still using to this day. We call it compositional symbolic execution now because we're using it for verification. But I think Pi 2 actually has some uses of the more original semantics-based compilation stuff now too. So.
Yeah, so maybe that's a good segue to start talking about Pi-Square a little bit. So when did the idea for Pi-Square first take shape? And what problem were you seeing that nobody in crypto was solving?
What really triggered the creation of Pi-Squared was probably unexpectedly, but it was investors. Because we realized we need a lot of extra resources to implement such an ambitious project. And we wanted to raise runtime verification back then, but it became pretty clear after a few discussions with investors. And by the way, maybe investors can learn something from this as well in case they listen to this. It became pretty clear that that runtime verification was not the right vehicle according to their criteria to invest, because runtime verification was already a well-established company, a legacy company. and they want to invest in new, fresh, sexy companies. I didn't like that at all. Actually, I stopped talking to investors back then. I thought that these guys don't know what they are doing. They don't see value where value is. But then we realized that actually it's not that difficult to spin out a company from runtime verification focused exclusively on execution, because that's what really PySquared is at this point. It uses semantics, not for formal verification like runtime verification does. It uses the exact same semantics, but for execution, for provably correct, verifiable execution. The other thing that led to us realizing that this is a big thing and we should do it was all this push for what the community calls verifiable computing. And that followed a very complicated path where you use a compiler to translate your program into some low-level ISA or VM language, and then implement a very specific circuit for that very specific ISA or VM. So the trust base is huge. There is a lot of room for errors in compilers, errors in ZK VMs. Also very, very slow, because you take one step with the execution of the program in the high-level language semantics, the original semantics, and transform that into hundreds of steps when you compile to RISC-V or even EVM. So we just thought that that was not the right way to do it. We thought that we should go through mathematical proofs and then generate zero-knowledge proofs. So mathematical proofs generated by the semantics, we already knew how to do that, we as a community. And there was just one little step left, how to take mathematical proofs into cryptographic proofs. And even that turns out to be a lot simpler and cleaner than compiling and having a ZK VM for your particular ZK VM. And we thought that that has a lot of merit as an idea, and it's worth implementing. And the idea is big enough to stand by itself.
Yeah. I remember the first conversation where I understood the Pi 2 vision was I was on the phone with Grigore at Amsterdam Dev Connect in 2022. It must have been the spring of 2022. Mm-hmm. And there we had been thinking, ZK was pretty hot, and, especially on the research side. And we were really thinking, like, how could we get involved in the ZK world? We were thinking of compiling K definitions to specific ZK circuits for each language. We had, the idea of compiling individual programs to circuits somehow using the K definition. But then Grigore, or maybe one of your students or someone had the idea of, actually using the mathematical foundations that we had in matching logic, rather than, making something that's kind of an engineering effort or an ad hoc compiler from K. And suddenly when that idea came, it was like, oh, this is obviously the right way to do it. There's no better way to make a ZK circuit for general program execution. And I think that's just become more and more clear as we did more experiments at RV while we were going through the raise process, and then as Pi 2 has been doing more experiments, it's just very blindingly obvious that this is the correct way to do it. So.
Okay, yeah, I definitely followed all the tech, definitely understood everything you guys were talking about. But for some people out there who maybe didn't follow everything, like, what are some practical applications that the verifiable settlement layer could, like, how should people think about it? Like, how is this going to solve a problem in crypto that exists today?
Okay, that's a very deep question. There are different levels of understanding. The easiest is to just think that all this is under the hood, right? When you drive a car, you don't care whether it's a gasoline car or a diesel car or even an electric car. You know how to drive it. Maybe it takes you a minute or two to figure it out, and then you can drive it from any point A to any point B, right? Which, of course, are drivable. So same here, from a normal user's perspective, there is no difference. You still execute programs in some programming language, and you get a result. You sign a transaction, done. Move to the next transaction, and your day. you don't care what's under the hood. But
well, I think actually, that's a really good analogy, because the problem with crypto now is that things aren't under the hood, right? It is that users are exposed to the details of, our contracts can't do that because it's Solidity. Our contracts can't do that because it's some specific Rust library or something like that. And Pi2 actually, the universal settlement layer, the universal, these actually move those details to under the hood, right? When you bring your own programming language, you bring your own paradigm for storage, you bring your own whatever, those details now are abstracted away. And I think that really is key. Like that really was what made it click for me, is the demo that was given at ETH Denver last year, where we saw, okay, you have a person interacts with a smart contract, partly written in Solidity, partly written in Rust. You're getting different features from the different languages, and the person doesn't see anything about the details of what's under the hood about that. They don't have to see anything that says like, oh, you can't do that because Solidity doesn't provide that level of abstraction, right? You can't do that because this is a Rust-based blockchain network, right? Doesn't matter, right? Like all of it, it's under the hood, right? So I think that's really the perfect analogy for why this is the right approach, because everything else where you're like, okay, we have a specific programming language, a specific SDK, specific way to interact with the blockchain or something like that, that means that's exposed to the user, right? They have to see, like, that has to be their mental model for how they work with the blockchain. But when you just say like, okay, we're gonna actually abstract these things away, we're just gonna have the general concept of claims, we're gonna have a more general way of making the blockchain work, right? Suddenly things become intuitive for the user, right? It's just very easy for them. I just submit the transaction, the payment goes through, the interaction happens, I make the borrow, whatever. Like, they don't have to think about the details.
Exactly, because the programming language, same like a car, is something that takes you from point A to point B. That's what a program does, takes you from state 1 to state 2. How it does that, all the different programming paradigms are less relevant. What's important is that you get a job done with the programming language. And the programming language, actually, I mean, that's my field. I spent 30 plus years working on programming languages. And if there is anything that I learned, is that programming languages are not such a big deal as many, try to make out of them. Yes, today we will have one language. Tomorrow we'll have another language. They change all the time, but in the end, they all do the same thing. Again, same like cars. They evolve, but they do the same thing. So yeah, programming language should not be hardwired in blockchains. You can just plug and play your language. Same like in a computer, right? When you buy a computer, you don't go to the market and say, please give me a Python computer. No, you don't do that, right? That would be stupid, right? So same here. Why should you have an EVM blockchain or a Rust blockchain or Python blockchain?
Yeah, and honestly, putting those details in, like an EVM blockchain or a Rust, whatever, it just makes things more confusing, right? Like it makes the idea of consensus more confusing. It makes the idea of storing data more confusing, right? And that's why blockchains that we are working with now today are so complicated, right? Like, I mean, they're not as complicated as like, the Linux kernel or something like that, right? They're simpler than that, right? But they're newer systems. They haven't built up that complexity, but they are complicated, and they're more complicated, and there are lots of groups that have been researching just pure consensus protocols, right? But then as soon as you try to take a pure consensus protocol and say, what's my execution layer? Okay, I'm going to try to do EVM, that reintroduces the complication layer. And so you need a way to abstract, to say like, okay, we don't care how you're doing your execution. You do it somewhere else, and you provide me the ZK certificate certifying that, the update is correct. That's all the consensus layer needs, right? And that's exactly what Pi2 provides.
And also, it's not hard to convince engineers that it would be great to use all programming languages. But when you talk to them, they immediately think that, well, then you need to bundle all these different VMs. You need compilers from all the languages to one VM or maybe a few VMs. They know how to communicate with each other and so on. And that's the moment when we roll our eyes, right? That's when we have an unfair advantage in the field, which is that we know you don't need all those. Once you have a formal semantics of the programming language, that's all you need to execute programs.
This is all becoming a very long-winded answer to your question, like how does this change the lives of the daily user? But I think I think the answer is a million paper cuts, right? And it's a million paper cuts that build up from doing things ad hoc, right? And when you're doing things ad hoc, you make one decision that makes it harder to make another decision, and you're building your own roadblocks into this. But when you take more of a formal modeling and formal semantics approach from the start, these decisions fall out naturally, right? They become very clean and easy. And so, like I said, the demo at ETH Denver last year, I think, was incredibly convincing, because it just showed, like, everything's simple, everything exactly how you expect it to be, but bring any language you want, and everything is natural in your execution model, and your bridge goes down, it's okay, it's recoverable, and it's everything how the user would expect it to be, rather than when I'm using DeFi now today, right? I'm like, okay, I want to go and do like a Aave-like loan on some other platform or something. Oh, that's not available, right? Because of some limitation of the Solidity language, or some limitation of how that other platform composes, or something like that, right? That's something I would expect to be able to do, and I run into this paper cut. Okay, so instead I unwind my position and pull out the funds, and I move it to the other protocol, and I do the thing, right? And so I've lost composability because we don't have everything in this formal basis where we maybe, that's one. And then I go to bridge my funds to another thing, right? And the bridge goes down, right? The bridge network goes down or something, right? Okay, as a user, why the heck do I need to worry about a bridge network, right? Like, what the heck is going on there, right? Well, with the Pi2 solution, you don't, right? Like, everything is supernatural. You can do it actually decentralized. You can submit your own bridge request, right? So like just a million paper cuts in the DeFi user experience are solved if you just step back. Like, how do we do this from first principles? We know what the goal is. We know we want easy access to financial DeFi primitives, right? How do we get that from first principles? And that's really, I think, what K framework into runtime verification into Pi2 is approaching it as.
Yeah, that's very interesting. I definitely we were having dinner the other night with my girlfriend and Daniel was talking about how he's studying Rust, and Brahman's like, "What's Rust?" Like, I'm like, "Is that the stuff on the iron?" I'm like, "No, it's a programming language." And I was just curious, honestly. I asked her, "How many programming languages do you know?" And she like sat there for a while. I was like, "Is C++ one?" I'm like, "Yes." It's like, "Do you know another one?" She's like, "No, I don't think so." So like expecting end users to know which wallet to use for Rust versus Solidity or whatever, it's not going to work. So I'm resonating with everything you guys are saying. And yeah, I think the demo from ETH Denver is really awesome. I think we'll include a link to make sure that people see that. All right, so what are the next steps for VSL? How can people start interacting? Or is any part of VSL live now?
Well, we have a DevNet. We have about 500 people who already registered to try it out, and probably have 500 more because we'll start publicizing soon. Please let your followers know that we are going to have this DevNet. And of course, all the RV folks are welcome to try it out. Then testnet in about 6 months, and then we go for mainnet early next year. So we are launching our network, which will be this set of claims and payments. And we build from there. I'm very curious. We are very curious to see how the field will evolve. But we believe that this is an important step to actually unchain the blockchains for a while and see how it goes.
So unchain the blockchains, it sounds like VSL, the verifiable settlement layer itself, is not going to be a blockchain, right?
Nope. No.
So, and will there be a token?
Yes, there'll be a token, definitely, because you need to power the economy. There will be validators, there will be service providers, there will be clients. They need to pay to each other for these actions. You need to have staking, right? So validators are incentivized to validate correctly. So there are lots of good things happening in blockchain. Don't take me wrong.
So I'm kind of curious, where will the token live, or like on another blockchain, or?
No, it will be on the VSL chain. Actually, it's exactly the opposite. Once you have a token on the VSL, so the VSL will provide native support for tokens and token transfers. There will be no ERC20 like contract, right? So that's actually important, which makes it particularly appealing for RWAs, the real world assets, and NFTs, and AI memes even. Right? So everything that can live by itself It's just a state that evolves and doesn't change others unless they explicitly communicate and have a protocol to do things together. It's a perfect application for this. And in particular, the fact that it mirrors different blockchains on it. It means that you can, for example, have a token or a meme or an NFT that can be sold and marketed on different blockchains, but it lives on the VSL.
Yeah.
Because each time you do a transfer or buy or mint a token on, let's say, Ethereum, that immediately gets reflected on the VSL, and now you can take appropriate operations there. Actually, that's how we intend to launch our token towards the end of this year, right before the testnet. The token will be on our own network, and people can buy it on any other network, any other blockchain that is connected to our blockchain, including on our blockchain. Sorry, take that back. On our set, and so it will be on set or on chain on different chains around.
I think the one thing that was said very quickly that actually offers quite a bit of power is kind of something hidden in there is that you mentioned, we don't need to, when we're trying to validate the block of a foreign blockchain, right, on the VSL, we don't need the prior blocks, right? We can actually just look at, pre-state, block, post-state as a compact and self-contained claim, and that I think ends up being a real key to very easy transference of liquidity between other blockchains, which is a huge problem right now, right? Like we have this issue, bridges are slow. You don't have pooled liquidity between your different, chains that you have assets on. You maybe want to take some sort of position out that uses that pooled liquidity or something like that. Then you have to have a fairly complicated network that is synchronizing all these chains, right? In order, if you are depending on all of the past data of a given chain, but if instead you only need to look at one block at a time, right? Then you can very easily determine, oh yeah, you did the appropriate burn on that chain. I don't need to look at all the history to know that you had the value up until you did the burn or something like that. You just take that one block, validate it. Okay, I can make the asset appear on the foreign chain. It's a way more efficient, way simpler way to be able to connect these chains together. And the most obvious application is this pool liquidity and hyper liquidity even, right? Just between different chains basically. But I think there's going to be, that again, like everything to do with blockchains and money and liquidity, that's the most obvious natural application of these things, right? And that's because it's just counting, right? It's money. But when you actually step back and you look at the mathematics and you realize, oh, this fast set thing, it's just relying on fundamental mathematical properties like the commutativity of operations. There's tons of things that can have commutative operations, and that includes AI agent inference, or it includes, self-driving car operations, or it includes, buying ski lift tickets or whatever, right? Like there's so many things out there that have that property that aren't just money, right? And so I think, the application, this really is something that can take, the blockchain, which was designed with money in mind. And so that's why we thought, okay, we have to have this sequentiality, right? And we generalize it and realize, oh, we can have all the nice things of blockchain, like the decentralization, the fast global knowledge of things for so many applications beyond just money.
Yes, exactly. As a matter of fact, we have a partnership with Wormhole, and we experimented together. What would it take to implement Wormhole using this infrastructure? The pain point of Wormhole is this network of guardians they have. They have 19 guardians, and they each have to run a full node on each of the blockchains they connect through Wormhole, which is a lot of pain. And that's why it's so hard to add a new blockchain. If you have a new blockchain and you want to connect it to Wormhole, forget it, right? It will be a year-long process or more, and you have to pay a lot. So we can replace that network of guardians completely by simply settling what happens on each blockchain on the VSL. And then whenever that is settled, you can take a proof that it's verified and validated and present it to the destination chain, and then you can mint the token there. So it's just a few lines of code.
Yeah, it's actually permissionless bridging, right? It's actually being able to take you don't have to rely on the fact that there's some network, the Wormhole network or whatever, existing for you to bridge your assets. You can take charge yourself. You can say, like, I'm going
to make it is so simple to do that, and actually that was our plan. Right? And then you can start wondering, why would I even need a bridge then?
But
because
to kind of
an application, you can just do a bridge yourself, adding a few lines of code for your application directly, and not take the risk that somebody may hack into the bridge and and you lose all the liquidity and so on.
But to push back maybe a little bit, if you're
Yes.
replacing those node operators, you're replacing them with something. Like in this case, probably like a
Our
set
network.
of verifiers, right?
Our
So
validator
those
network.
also have to be incentivized properly. And
Yes.
why, like maybe why is it easier to have this set of verifiers versus like node
No,
operators?
so suppose that you already have the network of verifiers. Suppose that you already have VSL, right? They already do the job of a blockchain, of a bridge. Actually, the way another way to look at our settlement layer is like layer 0 plus wormhole, everything in parentheses plus plus. Right, so you can do messaging of any kind, you can do transfers of tokens of any kind across chain, but you can do anything, basically any transaction of any kind with any meaning on any chain that is already mirrored.
But I guess I was getting at like, but somebody has to verify that, right? So somebody would have to have access to that blockchain to verify that what you're doing is correct. Am I understanding?
No. So our network of validators do that. So we plan to have like 1 million validators in our network because it's horizontally scalable. We add as many as possible.
That's key difference from other consensus protocols, by the way. You add more validators, they can slow down, as opposed to here, it speeds up. So
exactly. And also, of course, at some point you have to trust something, right? So in our case, we have to trust our network because otherwise, nothing can be trusted. But the same happens with blockchains. You have to trust their network. But we are going to have much more validators on our network than on others, and our execution of programs will be based on mathematical proofs, and correctness will be, held up to higher standards, let's say, than any blockchain actually around.
So the one thing I would say that is, so there's some network you have to trust, right? And here, this is the network of validators for the VSL, right? But that's going to be a network that is validating many more things than just bridging transactions. They're just validating general claims, any claim. Like this AI agent made this inference, they're validating that too, right? But in the case of bridging in particular, which I think is a major pain point for people who are in DeFi right now, there's several points of failure, right? And one of the points of failure is, the validator network in the middle, the bridge network goes down, or a relay network or the relay nodes on either end go down. Usually there's some sort of, there's people who are doing relay, they're watching for messages on one chain and they're relaying it to the validator network who's doing some sort of quorum signing, and then they're relaying it to the target chain, right? And so any three of those components can go down in a traditional bridging operation. Well, the middle component, that's actually doing the quorum signing and checking is it a valid transaction and sending it on, that's now the VSL, right? And so the VSL, which has a much broader purpose, and so we can assume it's robust in that regard, right? But the relayers, right? We don't need permissioned relayers anymore, and that's actually thanks to the power of ZK, right? So because of the power of ZK, you don't need the permission relayers. You can be your own relayer, right? And that's what that's what was demoed at the ETH Denver as the second demo that was shown there, right? So something where the internal network of relayers that are actually pulling the messages on Wormhole and pushing them to the target chain goes down. You can do it yourself. You can spin up your own little node, do the signing and the ZK certificate yourself. Everyone can check that it's valid and send it on its way. That's not necessarily unique to the Pi 2, but it does, combined with the fact that Pi 2 has this robust and fast network for settlement, provide basically instant liquidity sharing.
Yep. And another very interesting thing for going through semantics and assuring correctness is that now you can make formal verification play an active role in the execution of programs, as opposed to just being a post-mortem security auditing process, static process, right? Because let me tell you something that may sound completely unintuitive to your followers of runtime verification. You can do formal verification in order to execute your program faster and cheaper. right? It may look counterintuitive because formal verification takes money and it's done before. No. What is super cool when you go through mathematical proofs is that you identify opportunities, formal verification included, to get mathematical proofs of correctness of what a program does, okay, by engineering the actual mathematical proofs to a point where they can get shorter than the actual execution of the program. Right, an example that runtime verification, for example, worked on was Uniswap, right? We audited Uniswap, and one of the points there was to formally verify the square root function. The square root function is a while loop and calculates some fixed point, executing and computing division and multiplications, which are very expensive, especially for the ZK approach. Well, once you formally verify square root, you prove mathematically once and for all that this calculates the square root. That becomes a mathematical theorem. And now whenever you call square root, say you call square root on input 100, you can mathematically prove the square root of 100 is 10. In particular, that program will evaluate to 10 based on the formal verification proof. Okay, and that is only a few steps, just calling a lemma, which is already proved and settled, right? So now you just use it as a truth, and your mathematical proof will be minuscule compared to the execution of the program that has to compute and go through, all the iterations. And now you can actually have proofs and claims settled that go through mathematical proofs thanks to formal verification that are faster and cheaper, because it takes less gas, right, to validate the proofs because they're smaller than through execution, which is counterintuitive, but not to us. To us is the right, just more evidence that if you do things right, then everything comes together.
Yeah. This is very, very ambitious. What would you say has been the most technically difficult part of what you're building?
I want to say before you get into that, I know it sounds ambitious and crazy, and everything that we're saying is like we're trying to generalize everything, but I'm convinced in 5 years from now there won't be any other way, right? Like, because everything is so natural. Everything's so natural, it just falls so natural mathematically. And one thing that you said about formal verification leading to, more optimized code, or leading to lemmas that you can use, or leading to understanding your code better. Other industries are discovering that too, right? And that's something that, for example, AWS has a huge formal verification department, and they're trying to verify every single part of their tech stack. Every single part of their tech stack, they're trying to verify it. And why are they doing that? Because they're actually getting efficiency gains out of it, right? And when you're dealing with volume, and AWS isn't just dealing with money, right? They're dealing with like access control to compute. They're dealing with generalized compute, with generalized storage, all these things, right? When you're dealing at that volume, you have to have everything as efficient as possible. And formal verification does enable that. For them, they did a switch of their identity access management system over to a formally verified one, and it was 3 times faster. And that's because doing formal verification not only identifies the actual intent of your computation, right, so that you can express it more directly, right? It identifies places where your computation is doing something it doesn't need to do, because you have to explain all the details, right? So it's not surprising to me at all that formal verification leads to better efficiency. But I also just want to say, I know this is all like kind of, very ethereal feeling from the conversation we're having now about how this is going to go through. But I think it's worth learning about, because in 5 years, there won't be any other way to do it. The same as any other technology that's come along, and it seemed, kind of crazy at first. Like, when you start to actually look at how the pieces fit together here, it's very obvious. Like, there isn't a better way, right? And what you get is the right way to do it, right? So anyway, that was my
the main problem we faced, all of us, Everett, myself, and all our colleagues and collaborators, was performance. I even had very good friends now at Amazon, by the way, who told me like 15 years ago, when I preached the same ideas using the K framework as a basis for everything, they said, Grigore, this is beautiful, and I really like your vision, but this is never going to work in practice. It's always going to be dead slow. compared to handwritten compilers, handwritten interpreters, handwritten tools in general? Well, thanks to the effort of runtime verification, PySquared, University of Illinois, and many others actually around the world, now it got to a point where it challenges at performance, ad hoc, manually implemented, similar tools. So performance is not the killer of the idea anymore. And that was the last, missing piece. Now there is really nothing to stay in its way except us, putting the effort into it and bring it to light. And it's happening. And I think it will be faster than 5 years, Everett. I think in 1-2 years.
Yeah, I think so too.
Already wondering why should we do it any other way? Actually, we already talked to people. I already talked to many, even angels, former entrepreneurs who got very successful and now look at our technology, want to talk about it, see what we do. And when I tell them this, there's a moment of silence, and they say, "Why are we doing things any other way then?" And then I respond also with a silence, and then I say, "I don't know." That's how we should do things.
That's why I say 5 years, because there's the human element, right? Like you have to, just because the technology is the better technology, doesn't mean that the human element is overcome. But even if it's not runtime verification, it's not Pi 2, right? The beauty of mathematics and of science is when it's rediscovered by a different group, by different people, it's the same. It's the same as when it was discovered the first time. And so these are fundamental things that we have discovered and built and engineered the correct way from the ground up. They'll be discovered again the same way, right? And so that's why I say 5 years, 10 years, 15 years, whatever the amount in the future is, this will be the way that it's approached in the future, because it's just fundamentally more correct, right? It's a better approach to it.
Yes, and I think the step we made ahead from the previous generation that we are coming from is that we demonstrated that this is feasible. This is practically feasible. So as Everett said, even if runtime verification PySquared, bankrupt tomorrow, others will pick it up and do it, because everybody knows that now this is not only the right way to do it, but it's also feasible. And that brings me to what was the hardest part of the path so far, Paul, which was to improve performance to a point where people don't bring it up as the main problem of this approach. And I think we have passed that resistance threshold at this point.
Awesome. Okay, we're coming up on time then. My favorite question at the end is to ask for a song recommendation. I've been listening to a lot of Mau P recently. I know, Everett, I'm sure you'll enjoy his music if you don't know it already. But what do you guys got? What are you guys listening to?
Okay, so this is a little embarrassing, but I quit my Spotify subscription so I could send that same money to my local radio station instead. Because it's cool. It's like, not everywhere has like a local radio station that is like totally community volunteer driven. But on the radio today, there was a song, that song that everyone samples that has like "That Boy Needs Therapy," like that, that sample that they put into that boy.
I don't think I do, but
okay. Well, it's a really common sample that they put into it, but they played the actual original song, which is called "Frontier Psychiatrist" by the Avalanches. So it's kind of a fun.
By the Avalanche?
The Avalanches by
Avalanches.
The band is the Avalanches, and the song is called "Frontier Psychiatry." Or Psychiatrist.
That's interesting.
So.
Yeah. Okay. I didn't change much. I listen to the same music as in college, which is heavy metal or classical music, one of the two, depending on the mood and what I'm working on. But recently, I listened to a song which is completely out of my area of interest, but I really liked it, and then I listened to it several times. It's called "Within" by Daft Punk. I just liked it.
What's the name of the song again?
It's the "Within."
Within. Yeah.
Yeah, "Within" by Daft Punk.
Got it.
Ooh, also, I got another one for you, Paul. I went to a dance party on Saturday night and here in Moab, and the headliner was High Step Society, which is an electro swing band, and they're really good. If you want like some swing music with like kind of an electronic influence and really good vocals and singing and stuff, I would recommend this, High Step Society. And they're touring, so if you ever get a chance to see them live, they're really good live.
Awesome. All right. Well, DevNet is coming. We should all be excited to try it soon. Thanks for doing this, and maybe we'll catch up again after testnet is launching.
Wonderful. Thank you so much for having me.
Thanks so much, guys. Have a good day. This podcast is for informational purposes only. Views expressed are solely our opinions, not financial advice. Participants may have investments in the projects discussed.